Hi guys, we're about to look into the idea of number bases. It's a very interesting topic in maths, and we are going to focus on a brief introduction to number bases. Introduction to number bases. Alright, so there are calculations under this topic, but before we jump into the calculations, I want to make sure we understand the brief history and the concepts behind this topic. So let me begin from where we know or what we already know. I believe majority of us know that we work with the decimal system. We deal with decimal numbers, the decimal system. The decimal system is actually the most common system around us, accepted. We use it in the banking system, we use it in schools, we use it in writing and for in communication basically. So, but when we look at the decimal, what does that tell us? When we look at this word decimal, what does the word decimal tell us? The prefix deci here, deci, reminds us of what? There are some words that have that prefix deci. Examples of that word is the decibel. Examples of that word is the decimeter. Decimeter. So this is deci here, this is deci here. Now this deci is actually from Greek alphabet. Now another prefix that is related to this word deci is deca, and we see deca in a word like decagon. We also see deca in a word like a decade. Exactly, a decade is another prefix that is related. So these four words I wrote here almost have a similarity. For example, a decade indicates 10 years, a decagon indicates a polygon that has 10 sides, a decimeter is 1/10 of a meter. That is why in our metric table, when we are reading it out, we say 10 decimeter makes 1 meter. The decibel is also 1/10 of a bell. Now, just as a recap, this bell here, the bell is actually, that is BEL. BEL is named after Alexander Graham Bell. So in our physics classes, we write this as small d, capital B. Capital B indicates that it's the name of a person, just in respect or in regard to Alexander Graham Bell, or who founded the telephone, the first telephone that was used. So the decibel, like I said, is just 1/10 of a bell. So deca here is Latin, deci here is Greek. So you can see that from these, we can see that the decimal system it relates to a system that deals with base 10. That deals with base 10. Now, decimal system is also called the denary system, but we don't usually use that word. It can also be called also known as denary system. Denary system, but it's not a common word that we are familiar with, but you can keep it in mind just in case. The denary system. Now, it consists of 10 glyphs. That is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. These are the 10 glyphs that we can find in our decimal system. Now, when we make research into the history of counting, we realize that this decimal system that we have accepted did not just come by chance. There are a number of reasons that made us calm down, look at it and say, cool, among other number bases, let us pick base 10. Now, the decimal system is an extension of the Hindu-Arabic system. It's an extension of the Hindu-Arabic system. And the Hindu-Arabic system, for those of us that actually live in the Middle East and or are Islamic by religion, that means most Islamic people actually speak Arabic, they actually learn this the original, will I say, I would say the original Hindu Arabic glyphs, because there are certain way they write their numbers from 1 to 9. They have a certain way they write it, including 0. So they have a certain way they write that those glyphs. And initially, when you make your research, you realize that the Hindu Arabic system initially did not have up to 10 glyphs. They had 9 glyphs, but 0 was later added because 0 was actually needed by the Mayans. The Mayans came, they thought about it and said, oh, we need the number 0 to complete our counting system. If not, we won't be able to differentiate between 12 and 120, for instance, because 120 has an extra 0. 12 doesn't have that 0. So they added that 0, and the Hindu Arabic system adopted it, which later extended to what we have accepted as a decimal system, a system with 10 glyphs. You understand? So if we look at it, these glyphs, like I said, initially they had different types of glyphs in kind of different parts. The word Hindu Arabic system, let me say, this Hindu here indicates or comes from the language that Indians speak. I'm just explaining a brief idea of the number system so that when you look at the topic as a whole, you realize that there's a history behind it, and I believe you will actually appreciate the topic more. And the Arabic is actually the language that I would say the Middle East countries speak, like Dubai, that's United Arab Emirates, and those other close by Middle Eastern countries. So the Indian mathematicians were the first to come up with, these Indians were the first to come up with the system. So Arab mathematicians now adopted it and started making the adjustments. So over time, the glyphs evolved into what we know, what I wrote here as 0 to 9. But one thing that didn't change, which mattered a lot, was a concept called positional notation. Positional notation. This was a key concept that did not change. This was more like what made the Hindu Arabic system very special compared to the way other empires, other nations were counting in those days. For instance, from history, the Babylonians were said to be the first to the Babylonians they were the first people to use positional notation. Were first to use positional notation, but over time the Romans also used positional notation. But the issue with the Romans is that their positional notation was a bit limited. They arranged numbers in an order that increased in value from the left to the right. And if a lower number was behind or coming before a bigger number, they subtracted. If a lower number was coming in front of a bigger number, they added. So for example, in Roman numeral, or say the system the Roman used to count then, if you have they had these glyphs, uh their glyphs were one, they had V, they had X, they had C, they had L, they had D. I didn't arrange those ones, that's L and D, were they had M. So if we are common with our Roman numeral very well, we'll know that this I stands for 1, this V stands for 5, X stands for 10, C stands for 100, L stands for 50, D stands for 500, and M stands for 1000. So you can see that these were the only glyphs they had. And let's say they wanted to write 6. they will write 6 as VI. Now, VI, because the smaller number I is in front of the bigger number 5, it means 5 will be added to 1, and that will give us 6. But if they had IV, because the smaller number is coming before at the left, this was the kind of positional notation. The left right indicates subtraction and addition respectively. This is going to be 5 minus 1, which will give us 4. So this was what the Romans used. So, but this will be very cumbersome. For instance, if you want to write a number like large numbers like 1996, it will be cumbersome. It will be cumbersome or stressful. It will be exhausting. So, but still, the Romans were smart because the system before them was the unary system. And what was the unary system? It's actually a system in base 1. Base 1. That means you just count in 1. Either you use sticks or use parts of the body, anything that represents 1. 1 will represent 1. Let me say 1 represents 1. 1 1 will represent 2. 1 1 1 will represent 3. 1 1 1 1 1 1 will represent, that is 6. So most times tally was used 1 1 1, then they will cross, and this will represent 5. So all this idea, even the idea of tally, this is involved in the unary system. There's only one glyph, and that glyph is 1. So, but our system now is the best when you look at it. We use positional notation, and let me just explain what that means. Positional notation simply involves a kind of system of counting. It's a system of counting where the system of counting where the value of a digit or a number, value of a digit depends on the position, depends on the digits, let me say the digits multiplied by, this is how we can easily define positional notation, where the value of digit depends on the digit multiplied by the factor. Let me clean this. By a factor which is determined by the position of the digits, and the base. Good. So this is basically what positional notation is all about. So for example, let me give you an example of what we are talking about. 5 5 5 in base 10. We have the same digits, but since we are in decimal, believe this, everybody should be familiar with this. We indicate that this is our units place, this is our tens place, this is our hundreds place. So the value of the first 5 here is not just 5, the digit is 5, but the value is 5 multiplied by factor. And what factor is that? 100. The value of the second 5, which is this, the first 5 gives us 100, that's 500. The second 5 here, the value is given by 5 multiplied by what factor? 10. That is why we indicate C here. The third 5, which is this, is under the unit place. So the value is given by 5 by 1. So when we add this, we get 500 plus 50 plus 5. Now, we realize something, that as we progress from one position to another, or we can say from one place value or placeholder to another, we are just going, the difference between the factors, which is this 1, 10, and 100, is only in the powers. We can still express this 100, 10, and 1 as powers of the same base, which is the base 10, the decimal. Remember that this is base 10. This is base 10. 10. Good. So I can still rewrite this as, say, 5 times 10 raised to the power of 2 plus 5 plus 5 times 10 raised to the power of 1 plus 5 times 10 raised to the power of 0. So you can see. So we move from, which means the first, we are counting our positional notation. In our present day positional notation, we count from the left, or rather from the right to the left, in increasing value, and the base remains the same, but the powers are increasing. The shift from 0 to infinity, depending on how large the number can be. So as a quick example, another example is this: 2 on 2 3, let's say 237 in decimal. 237 in decimal. In this case, how can we write this in its expanded form? For us to write this in its expanded form, because that is basically what we are doing, just to be able to understand where all this comes from. In expanded form, this is going to be 2 times, remember, we move, the powers increases from right to left, so we have bigger numbers as we go in this direction. So go in this direction. Okay, so basically this is going to be 10 raised to the power of 0. This is going to be 10 raised to the power of 1. This is going to be 10 raised to the power of 2. I hope we get that. So this is 2 times 10 raised to the power of 2. Remember the definition, because we are multiplying by a factor, plus 3 times 10 raised to the power of 1 plus 7 times 10 raised to the power of 0. This is the simple answer. That is 237 in its expanded form, or which we can read as 237. So the question people can ask is, why did we pick base 10? Just like the question I was asking in the beginning. It's because when counting, most times it's easier to learn counting of numbers and writing of numbers by using our fingers, and we have 2 hands with 5 fingers each, so we have 10 fingers. So since we have 10 fingers, it makes sense to adopt a system that is base 10. However, some people and some mathematicians claim that if we are working with a base 12 system, it will make our calculations easier. They have a point. Why? Because, for example, the multiplication table would have been much easier and much faster to learn, since 12 has many factors. 12 is divisible easily by 2, 12 is divisible by 3, 12 is divisible by 4, 12 is divisible by 6. So these are factors of 12. We have many. Unlike base 10, 10 is just divisible by 2 and by 5, and of course by 10 as well. So that is why it's easier in our base 10 system when we are learning 2 times table and 5 times table. If you've learned your multiplication table, you get what I'm saying. 10 divided by 3, for example, is giving us a decimal. So you get the idea, 3.3333. So this is their claim, which makes sense. But the issue is, we are already used to our base 10 system. It's very difficult at this point. It's not like a habitual something to break from the habit of counting in base 10, multiplying in base 10, doing division in base 10. and all that. So the other bases we are going to look at include our base 2 system, the base 2 system, which is also called the binary system. We are going to see this base very well when we begin to solve questions in other videos. The base 2 system is a binary system. The prefix here, bi, will help you know, remember the base. When you remember biennial, when you remember bimodal, most words that begin with bi, like bisect, to divide something into two in construction. So this is base 2. Even though they don't give you the 2 and you see binary, just know that it is base 2 system. It has only 2 glyphs or 2 symbols, 2 digits, 0 and 1. These are the only 2 glyphs in the base 2 system. But we use the same idea of positional notation. So for example, that is in this base 2 system, if we are to write 1011 in expanded form, so I'm using this as a test now to see if you have gotten my explanation so far. 1011 base 2, you see a small 2 here. This is the way the number comes. Just to help you know that this either 2 is written in this form or is spelled out in words TWO in expanded form. In expanded form, what do we get? Expanded form. Good. So remember what I said, that the base remains the same. The value of the numbers increases as you go from right to left. So the first one here is going to be 2 raised to the power of 0. The second one here, we have the value of 2 raised to the power of 1. This will be 2 raised to the power of 2. And this one will be 2 raised to the power of 3. So in expanded form now, we can write this as 1 times 2 raised to the power of 3 plus 0 times 2 raised to the power of 2 plus 1 times 2 raised to the power of 1 plus 1 times 2 raised to the power of 0. Now, this is the answer. Very simple. Some people usually omit this one, anyone that has 0 here, and you can't blame them, because 0 is just a placeholder to represent nothingness. That is nothing in that placeholder, meaning there's no value there. So what's the point adding it when 0 multiplied by anything will still give you 0? So as we move forward, I will introduce you to another common base, which is base 8 system. The base 8 system is also called the octal system. The octal system, and it has 8 glyphs. And what are the glyphs? You can guess: 0, 1, 2, 3, 4, 5, 6, and 7. Alright, so the base 8 system, let's say for example, we are to write 4, 5, 7 base 8. You see the 8 small, it's a subscript on the number. If we are to write this number in expanded form, okay, I think this one will be very easy now, since we have done for base 10, we've done for base 2. Good. So in this case, remember the values increases from the right to the left as we go in this direction. The first one is going to have a factor of 8 raised to the power of 0. 8 raised to the power of 0. This one will be 8 raised to the power of 1, and this one will be 8 raised to the power of 2. So in expanded form, this will be 4 times 8 raised to the power of 2 plus 5 times 8 raised to the power of 1 plus 7 times 8 raised to the power of 0. Very good. So this is how it's going to be. So we also have the base 16 system, and this is the last system we are going to look at for today before we end the class, which is also called the hexadecimal system. The the hexadecimal system. It has 16 leaves. So base 2 system has 2 leaves, 8 system has 8 leaves. This one has 16 leaves. So we have, I will write them. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, now 12, 13, 14, and 15. Now take note of something. From this 10 down to 15, to avoid a confusion, let me highlight them. From 10 to 15, we have special symbols for them. We don't write them like this to avoid confusing 15 in base 16 with 15 in base 10. You get my point? So what do? In place of 10, we use A. In place of 11, we use B. In place of 12, we use C. In place of 13, we use D. In place of 14, we use E. In place of 15, we use F. So for example, if we are given, for example, we want to write, let's say 5A7, and you see the base 16 small here. In base 16, in expanded form, now I'm very sure you've done this one on your book already, or even in your head. So because we already know that the base is 16, the values will increase from right to left like this, and we know that the power will start from 16 raised to the power of 0, 16 0, this one will be 16 1, this is 16 to the power of 2. So we are going to have 5 times 16 raised to the power of 2. We use our brackets to make our work neat. A, remember we know what A is representing. A times 16 raised to the power of 1 plus the last one, 7 times 16 raised to the power of 0. So these are the 4 bases. Are they up to 4? Okay, 2, 8, 16, and 10. Exactly, they are up to 4. These are the 4 bases which we will look at today. We have other bases. We have the quinary system. Let me just introduce these ones before as I end the class. The quinary system is the base 5 system. Is base 5. We have the ternary system. Ternary system is base 4. We have the quaternary, like from the word quarter, quadruplets. Quaternary system is base, hey, I made a mistake here. Our ternary is actually base 3. Our ternary is actually base 3. Okay, and our quaternary is actually base 4. Exactly. So these are other examples of systems we have. The base 12 system is also important. It's called the duodecimal system. Duodecimal system. It is base 12. The Babylonians used very intriguing and high base, which is base 60. Sexagesimal, that's what it's called. Sexagesimal system. It's what the Babylonian used, and that is base 60. And because of this base 60 that they use, we rely on this base 60 in our clocks, time reading, that is why we say 60 seconds make 1 minute, 60 minutes make 1 hour, and like that. And even in maths, we use this sexagesimal system in maths. When we are calculating angles, we say 1 degree is made up of 60 minutes and 1 minute is made up of 60 seconds. So Thank you for watching. If you have any question, please leave it in the comment section and I will do my best to answer. And try to subscribe so that you'll be informed or notified when we post questions, because there are different questions under this topic. There are different calculations under this topic. Conversion is the next topic we're going to look at. And we'll look at addition and subtraction, multiplication and division. So I would love for you not to miss any of this.